Hi, and welcome back to the CuSi Sound channel. When I did my 2020 vision vlog at the start of this year, I was looking forward to some of the ideas for projects I had for the coming year. One of the ideas was to see whether I could design, build and actually get working my own version of a clock divider. Yeah, there's plenty of circuits out there that other people have done that have been tested and proven, but I wanted to see whether take what I've learned over the last 14 months and apply that admittedly basic knowledge and build something that I've designed and hopefully got working. So the core of the design is to use the 4017 decade counter that's in the Baby 8 sequencer, because I've built a few of those circuits now and I kind of can get them working okay, but then to use a rotary switch such that by turning the switch I can get the counter to reset at pre-selected steps around the switch. You take the output from the first step, you can kind of extend the time it takes to get back to the first step and the output by how many steps have to be counted before it resets and you get the output again on step one. So that's not a new idea, that's been done by other people, but yeah, that's kind of it's a sound theory in itself. One of the other things that people have found is that when they use things like the 4017 decade counters as a sequencer, if they want to use it for getting gate outputs within sequence steps, you don't always get a clean break in between steps, so you don't get a kind of a longish pause, so you go from high to low and going back up to high, you can sometimes get a bit of a overhang. So what I'm looking for is kind of get something that looks more like a clock pulse, so it is a pulse. The way they get around this is they take the input from, well, they start with the output that they're getting from the decade counter, but then they take the output from the clock. So you've got decade counter, then the clock that's driving the sequencer, and only when both of those are high do you get a high output. Now that's an AND gate, because you've got to have clock and sequencer high for output to be high. So if you've got a nice sharp pulse on your clock, as that drops back to the zero, even if your sequencer is high, your clock's gone low, so your output on your AND gate will go low. And I thought, well, I could use a logic chip, which is what most people do, but then because I'm kind of trying to learn more about theory, I thought, well, can I actually build an AND gate using transistors? And yes, you can. That's kind of where they came from. The basic theory is there. So again, I looked up the basic theory, found a relatively simple circuit. I thought, right, this is, I've got the decade counter thing, so let's see whether I can do something on the AND gate side of things. And so I decided to breadboard up a transistor AND gate, and here is what happened. This is the transistor AND gate circuit as built onto the breadboard. This is the schematic of the circuit, so you can see what it is. It's basically two transistors in series. So the transistors are, consider them acting like switches, so you've got two switches in series. If both of the switches are closed, then the current will flow. If either of the switches or both of the switches are open, then you've broken the circuit and you won't get an output, the current won't flow. So this is basically what we're getting the transistors to do when we are building it as an AND gate. So what I've got here, I've got the transistors I've used are 2N2222 transistors. The power into the collector on the first transistor is coming from the 9-volt battery. The logic inputs A and B are going into the bases of the transistors, and they're going through 10k resistors. The emitter of the first transistor is connected to the collector of the second transistor, so that's kind of the switches in series kind of theory behind it. And then the output from the emitter of the second transistor is where we get the output, which is going via a 4.7k resistor down to earth. But I've also put a diode on there with a current limiting resistor, and as an input I've got a battery pack here that is going to be providing 6 volts. So if I make input A high and input B is low, then the output is low, the LED is not lit. The theory says that if I make input A low and input B high, then the output should be low. What's happening here, I'm not 100% sure about what the theory behind this is, but basically what's happening here is that I'm getting a small output when I put the 6 volts into the base of the second transistor. I think that's just because I'm getting something carrying through to the emitter there. When I actually measured what the output was that was providing this dimly lit LED, it was about 1.6 volts. So I would take that out. Now the theory is that if I make A high and B high, then output is high, and there you go. You see the LED is really brightly lit now. And when I measure that, I'm getting something like around about 6 volts. So apart from the slight bleed through, which depending on how I wire this into the circuit and which outputs I use from the clock and the counter, the decade counter, depending on how I choose to use those outputs, it shouldn't really matter if I have a low voltage on one of them, because it probably won't be enough to trigger the reset on the chip. So I should be able to get away with it. It's a bit crude, and it would be a lot more accurate if I actually used a logic chip, but you know, where's the fun in doing what's already been done? Well, you know, I'm experimenting and I'm trying things. So I'm relatively pleased with this. I think that yes, using 2 transistors, I can build an AND gate to use in my simplified clock divider. So yeah, come by at a later date, and who knows, you might see a functioning clock divider at some point in time. But this is a work in progress. It's an ongoing project, and yeah, there could be updates, and like I say, eventually a working clock divider.